most important theorem on system of linear equations states that the existence of solutions of a system of linear equations is equivalent to the rank of two matrices to be equal. Therefore, it is crucial to be able to compute rank of matrices that are explicitly expressed through numbers. The rank of a matrix, in a sense, gives the magnitude of the matrix. The magnitude of the matrix is not simply the number of rows or columns. The rank is more related to the content of the matrix, the magnitude of the content of the matrix. So the null matrix is a matrix that whose all the rows and columns are zero vectors. So it does not contain any data, although might be arbitrarily large as a matrix. On the other hand, the identity matrix contains a lot of data, and this is detected by the concept of rank. So let's give again the definition of rank of a matrix. So let M be a matrix. The rank of M is any of the following four statements. So can be the maximum number of linearly independent column vectors of M, or the dimension of the vector space generated by the columns of M. These two are the same. Now it is crucial that here we consider the maximum numbers of linear independent column vectors. Typically, when some student is being asked the definition of rank, they are going to say the number of linearly independent column vectors. But this, of course, is not a well-defined number because it depends by how many vectors I consider of the matrix. So if I take the maximum number of linearly independent column vectors, this is a well-defined positive integer, and it is defined to be equal to the rank of the matrix M. But it can also be expressed as in terms of row vectors of M. So it is also the maximum number of linearly independent row vectors of M, which in turn is equal to the dimension of the vector space generated by all the rows of M. To prove that these two definitions of rank are consistent, so they both define the same number, it's a theorem. I mean, it's not something completely obvious. Okay, so, but since it is true, I'm going to set the definition of rank using both of these statements in terms of column vectors of the matrix or row vectors of the matrix. Let's see a few examples. Let's consider first the null matrix. So you see all the vectors, column vectors or row vectors are zero vectors. Therefore, the vector space generated by them is just the trivial vector space reduced to the identity element, to the zero. Therefore, its dimension is zero. So rank of the zero matrix is always going to be zero regardless h and k. Now, at the other extreme, we have the identity matrix. Now, the identity matrix is a square matrix with ones on the diagonal. This was the identity element for a matrix multiplication. And as we see, if we consider the rows of this matrix or the columns of this matrix, we obtain a set of vectors which constitute the canonical basis of R to the k. Okay, so being a basis, the vector space generated by these vectors is the whole vector space, so it's going to be all Rk. Therefore, the rank of this matrix is k, so it's the maximum possible rank. Let's consider more in general a diagonal matrix, which is a matrix that has zeros on the upper triangular part and zero on the lower triangular part. Okay, let's call A11, A22 through AKK the coefficients on the main diagonal of the matrix. Now what's the rank of this matrix? The rank of this matrix is easily seen to be the number of non-zero elements along the diagonal of this matrix. Now notice the following very important fact. Now from the very definition, we will see that the rank of a matrix cannot exceed the minimum between H and K. Okay, since it can be defined in terms of column vectors of a matrix or row vectors of a matrix, it cannot exceed the minimum of these two, which H is the number of row vectors and K is the number of column vectors. Of course, then can be 0 in for any choice of H and K, and this is going to be 0 if and only if the matrix is the null matrix. But the maximum rank that a matrix in MHK can have is going to be the minimum between H and K. Now there are other matrices for which it is very easy to establish what the rank is. This broader class of matrices is called matrices in a row echelon form. So what is a matrix in a row echelon form? So it's a matrix for which the number of zeros at the beginning of every row strictly increases as the row index increases. In order to understand better what this amounts to, let's see an example. So suppose we have a matrix, and the first row of the matrix starts with maybe some zeros, let's say a couple of zeros, 0 here and 0 here. And then there is a scalar which is non-zero, let's say 2. Okay. And then it just continues with other scalars we are not caring about, because this will not affect the fact that the matrix M will be in row echelon form or not. Okay. Now, if we want M to be in a row echelon form, we want to make sure that the second row will have a number of zeros here on the left that will strictly exceed 2, because 2 is the number of zeros that the previous row has on the left. Okay. So the second row will have to start with a 0 here, a 0 here, and also a 0 here. So it must have at least 3 zeros here on the left. Let's say that it has a few more ones, and then it has a non-zero element, -1, at some point. Okay. So these two rows fit in a row echelon form matrix. So let's see what the third row must look like. So remember, the number of zeros at the beginning of every row strictly increases as the row index increases. So now we are looking at the third row. Now the third row must have a number of zeros here on the left that will have to strictly exceed the number of zeros of the previous one, right? So we'll have to be 0 here, all the way through here, and also one step more here. Okay? And then it continues as doesn't matter in which way it continues, and so on. If we consider the last row, now the previous one will not be expressed as a linear combination of the last row. It's not going to be a multiple of the last row, because the previous one will have a non-zero element, here in this case is -1, where the last row has a 0. Therefore, there cannot be a multiple of this row that can be equal to the second to last row. If we consider the last two rows, then all the linear combination of the last two rows will have 0 in this position, in the position where the third to last row has a 2. Therefore, this third to last row cannot be a linear combination of the last row and the second to last row, and so on. So one can easily, by recurrence, show that the rank of this matrix is going to be equal to the number of non-zero rows. So rows are vectors, so here non-zero means non-zero as vector. Okay. Therefore, it is very easy, once again, to find the rank of this matrix. Now, the idea is the following. Let's assume that I have a generic matrix. A generic matrix cannot be expected to be of row echelon form. But suppose that I'm able to produce a certain transformation on this matrix, which at the end they will reduce the matrix to a matrix in row echelon form, and each of these transformations will leave the rank unchanged. Okay? So that will provide a technique to compute the rank of a matrix. So we start from M, and then we reduce with several transformations, and then at some point we get to another matrix which is in row echelon form. We know that this last matrix will have exactly the same rank as the beginning one, and the rank of this last matrix will be obvious. We can just look at the matrix and find out what the rank is. Okay, so this is exactly what happens in practice. Let us talk now about these elementary row transformations, also called operations. Let's give a definition of them. There are three kinds of these operations. The first consists in switching two rows of the matrix. The second one is multiplying a row by a scalar lambda, which is non-zero. And the third consists in replacing a row Ri by the following row that is computed by taking Ri again and summing a multiple of another row Rj. Rj might be all Ri itself. In this case, it will be just the operation number 2. So if Rj is again Ri, we can just factor out Ri on the right, and we will have here on the left a scalar multiplying Ri. So it will be just the operation number 2. Now, the importance of these operations is the following. Elementary transformations leave the rank of the matrix unchanged. Okay, so as long as I operate or I apply this elementary transformation to a matrix, the rank will not change. A fundamental remark on elementary transformations is the following. Let T be a row elementary transformation and M a matrix with H rows and K columns. Then if I apply the transformation T to M, any of these ones, 1, 2, or 3, I will get another matrix, which we call T applied to M, T with M between parentheses. So this matrix is exactly the same as taking M and multiplying on the left by a certain matrix. Row transformations, elementary transformations, reduce to left multiplication by a certain matrix. Now, what is the matrix we are multiplying by? Is the identity matrix to which we applied the same transformation T. So in the next lecture, we will state the main theorem that relates elementary row transformations to row echelon form of matrices.